In your previous light videos, we sort of looked at the particle model of light. Really came up from Newton and his work, and we looked at the experiments that were done to try and find the speed of light and show that it actually existed and some of the stuff like that. So now we're going to start looking at the wave model of light, or the wave theory of light. And there's a few things we can look at that. Basically by the early mid 1800s, it basically had replaced the particle model of light for a variety of different reasons. By the early mid 1800s, there was a lot of things that they could explain using the wave model of light, that light travels like a wave. So they could explain most things, like the reflection, refraction, all that kind of stuff. They could explain most things that light did. They had, of course, Snell's law of refraction, and they could explain why light changes direction. They could explain reflection easily, dispersion, getting the different colors. There's a whole bunch of different things that they could actually explain. The change in speed using index or refraction. So there's lots of things that they could explain. There's not too many things that they couldn't actually figure out. But there was one thing that was really, well, there's a couple things, but one of the problems that they had was the whole rectangular, erase that a little bit, that's better, rectangular propagation of light. Okay, for some reason, why didn't it, when it went through an opening, why didn't it actually diffract? Like when waves go through openings, waves spread out. So why is it when light goes through an opening, why doesn't it spread out? Why doesn't it actually diffract? Now, to figure this out, we have to go back in time a little bit, actually to the 1600s. So we're going to go back a little bit to the 1600s. And in the 1600s, there was an idea that was introduced by a guy named Huygens. And some people say Huygens, some people say Huygens. You'll hear different pronunciations, whatever. Okay, but a couple hundred years earlier, there's a guy named Huygens who he actually worked on waves and how waves worked. And he actually had a really neat idea of how waves actually move and do different things. Okay, so to explain his idea or theory of how waves worked and waves move, we're going to use this car right here for a second. Now, that's a 1969 Plymouth Fury. I know, because that was the first car I ever had, was this 1969 Plymouth Fury. And what a fantastic car. It was a giant car. If we were in a regular class, we could have stories about how many people I could fit in the trunk. It was actually very impressive. But anyway, that is something entirely different. Anyway, so suppose we have this car. Suppose you're watching this car, and what happens is the car we're going to copy and we're going to paste it. So there we go. So there's that. There we go. So I copy and paste it. Now suppose I copy and I pasted it, and the second picture showed up right in front of it. But as soon as the second picture showed up, the first picture just disappeared. Okay, so it was just gone. And then I press paste again, and it pasted right in front of the other car. And as soon as that one showed up, this one would disappear. Okay, and we kept on doing this. So I'd paste the car car would show up right in front, and as soon as that one would show up, the other one would disappear. Now, if we kept on doing this and doing this, what you'd see is the car, you can only see one car at a time, because as soon as one is pasted, the other one just disappears. And as it keeps on going, you'd see this car, all of a sudden you see one pop up here, and then pop up there, and then pop up there. So if we actually started from the very beginning and did this really quickly, it'd be like car, 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 and it would just keep on like that. Now, the thing is, obviously you can see, it's sort of jumping. But what if it didn't happen so slowly? What if it happened really, really, really quickly and the car was much smaller? Well, then it would actually look like the car is actually moving forward when it actually isn't. Like maybe instead of it showing up right in front of it, it would show up just a little bit further forward, but they wouldn't overlap, because as the second car shows up, the first car would disappear. So you only ever actually see one car at any given time. And it would look like the car's actually moving forward if we kept on pasting and pasting and pasting, but it actually isn't, because every time we paste the car, it's not the same car that we just had. So it's always a new car every single time, okay? So it looks like the car is moving forward, but it's not. It's just paste after paste after paste after paste. And when you're pasting the new car, the old one disappears, okay? So that is the idea that Huygens had of how waves actually travel from one place to another. Basically what he said is that waves actually recreate themselves. And just the way the car recreated itself. We took the car and we pasted a new car, but then the original disappears. And then a new one's pasted and the original one disappears. And it's pasted again and the previous one disappears. He said the same thing for waves. He said the waves actually recreate themselves. And because of this, they appear to move. But the waves aren't actually moving because the previous wave isn't the same wave you had before. The same thing with the car. It looks like the same car is moving forward, but it's not. It's actually a different car. So he said waves recreate themselves and appear to move, but they don't actually. If we get more specific, what he said was, he said every point on a wavefront, remember the term wavefront from before, is actually a new point source. Okay, so let me sort of explain how that works. So let's take this right here. So suppose you have some waves. Okay, so there's some waves, and the waves are going this way. What he said was the waves aren't actually moving. The same thing with the car. It looks like it's moving forward, but it's not. But here I'll show that every point in a wavefront idea. If we go onto here, he said on here, this isn't just one big wave. He said there's a whole bunch of little point sources on it. And I can't draw infinitely many of them, but something like that. There's a whole bunch of point sources. Now, when point sources give off waves, like throwing rock into water, the waves they make are circles. And each one of these guys is giving off circular waves. The thing is, what happens inside of here is due to geometry and symmetry, everything cancels out. And all you end up seeing is the sort of the added up crests at the very, very end that make a flat layer, which makes it look like a new wave when it actually isn't. Okay, so it's kind of abstract, kind of weird to think about and visualize, but this is what he said. So when you have a wave, there's actually all these little point sources on the wave. Each one makes a circular wave. All the stuff cancels out except for the very, very front. That builds up, and that's what you actually see. And this happens over and over and over and over again, repeatedly, with infinitely many points, infinitely small. It keeps repeatedly happening all the time. So it looks like the wave is actually moving, but it's not actually moving. The wave actually lasts for an instant in time, and it creates a whole new wave right afterwards. Same thing with the car. The car lasted for an instant in time. It disappeared right when the new one was created right in front of it, and it kept on going. Okay, so it's kind of, I know it's kind of weird, kind of abstract, but this is what he said, and this is how he said waves actually move from one place to another. Okay, so the thing is, this helps to explain the whole thing of why light, when it goes through an opening, it typically goes straight. And I want to show you some pictures to sort of help us out with that. Okay, so here we have a little picture here. We got some waves coming down. So those are the wave fronts coming down. Okay, and those waves are going to hit a barrier with an opening in. So there's you see the sides there, there's the walls, and there is the opening. And if you remember what you guys did before, if you want waves to go through an opening and you want them to spread out really, really, really good and really strong, the waves and the opening need to be about the same size. And you can see here the opening is way bigger than the waves are. So let's see why then it doesn't work. And if you remember when we did the simulation a videos ago, the waves came through, but the middle part was really flat. Well, let's see why. If we apply Huygens principle to this, okay, there we go. So there's the wave there, and these little yellow dots, those are the point sources. So I've sort of drawn little point sources in there. So it's not just one wave. That wave is made up of a whole bunch of little point sources. Each one of these little point sources is going to give off circular waves. And if you do that, you get a kind of a complicated interference pattern. And you guys have done interference patterns before, and it ends up looking something like this. Okay. So in the middle part, because these guys are all lined up side by side, the interference pattern, the constructive interference, ends up giving a really flat section here. The side part's still curved because you got the curvature from these guys on the edge here sort of dominating. So you still get curvature on the sides, on the left side and the right side. But in the middle, it's pretty much flat because you got so many guys side by side. The overall wave is generally flat. So it's pretty flat. Okay. Now, what if we change this a little bit? Let's take the exact same type of thing, except now make the opening smaller. If we make the opening smaller, about the same size of wavelength, what we do is restrict how many of these little point sources will fit. And if we make the opening small enough, it basically fits one point source. Well, if you have only one point source, your overall waves are going to be a lot more circular. And this is why diffraction works best when the waves and the opening are about the same size, because you're restricting how many point sources are in there, and you end up with just generally one-ish point source, which gives really good circular waves. Okay, so if you remember, opening too wide, too many point sources side by side, you end up with a flat section in the middle. If the opening's way too small, you just restrict the amount of energy. You still get good, spreading, but most of the energy is being blocked. Okay, so this is why you can't have light spreading out through most openings, because light waves are so incredibly small, they didn't make the connection that the openings were just too big. And that's why when they're doing early experiments, the light waves were just way too small, the openings were way too big. So for most of the experiments they started with, they had something like this, where most of the energy went straight through, because to make the openings as small as a light wave was very, very difficult to do. Okay, so let's go back to this here. So this explained why the whole d lambda type thing. So basically in the early experiments, so in the early trials or early experiments, basically the openings were way too big, so the light actually went pretty much straight through, and that's why they didn't really notice that diffraction thing, because the openings were way too big. And the thing is, when this idea came out, when he actually proposed this in the 1600s, it wasn't actually connected to light. Okay, because back then, in the 1600s, light was thought to be a particle, so there was no reason to connect this to light theory, because in 1600, they thought light was, right, kind of small here, light was a particle. So since light was considered to be a particle around this time, there was no reason for them to connect this idea to what they were working on. It wasn't until later on, when they're really trying to develop the wave model of light, they went, hey, let's go back a couple hundred years to this really cool idea that this guy Huygens had and see if we connect it to light. And once they connected to light, they could explain that whole diffraction thing. Okay, so it's a kind of a weird idea, the whole Huygens principle idea, that waves don't actually go from one place to another the way people think they do. They're always being recreated. So it's not the same wave that you had previously. It's actually been recreated. It may have similar properties or identical properties, but it's not exactly necessarily the same type of wave. Okay, and we'll look at that a little bit more in the next video and then some applications of it.